Welcome to next lecture on torsion. Today we are going to see how torque T is related to the Prandtl stress function. Stress function P. So in previous lectures what we have seen that tau xg is equals to dou phi by dou y and tau yz is equals to dou p by dou x. It is negative dou p by dou x. So this p is Prandtl's stress function. From this we derived one equation, dou square p dou x square plus dou square p dou y square, which is equals to minus 2g theta, and we call this equation Poisson's After that we have seen that how this P is changing on the boundary of the shaft. So for that we have considered this element ds, and we have seen how Prandtl stress function is varying on the boundary, and we found that d phi by ds is equals to 0, which means P is constant on boundary, and generally P equal to 0 is taken for problem solving. Now in today's lecture we'll see torque derivation in terms of P, Prandtl stress function. So for this we'll draw again one general cross section, x axis, y axis. This is the elemental area dA. The coordinate is xy. Length of this element in x direction is dx. Length in y direction is dy, and we know stress components tau yz and tau xz are acting on this area. This area is dA. So when we apply the torque T, the resistance dm is getting generated in the cross section, and this moment will take it around this center O, and what we can write is tau yz into dA. This is the fourth term, into lever arm, which is x direction. So into x. Now this yz is counterclockwise, means we are taking this moment as positive moment, and then xz is in clockwise direction, so we'll take it as a negative. So tau xg dA is force into lever arm y. Total moment of the resistance offered by cross section is equals to integration of dm over area A. So area of this cross section is A, which will be equal to applied torque. Therefore T is equals to integration of tau yz x dA minus integration of tau xg y dA. This whole integration is over area, and now we know that dA is equals to dx dy. Therefore T is equals to integral over area A of tau yz x dx dy minus tau xg y dx dy, and tau yz is equals to dou p by dou x minus, and tau xg is equals to dou p by dou y. So putting these values of tau xg here in this equation, we can get T is equals to integral over area minus dou p by dou x into x dx dy minus integral over area A dou p by dou y into dx dy. So when we integrate these with respect to x using integration by parts, we can write this as taking negative side outside. So first term as it is, and integration of second is p, and you can write dy. So this is over boundary of the cross section minus integration of d by dx of x is 1, then integration of dou p by dou x is p, and dx dy. So this is again over area A. Plus y into pi dx over boundary of the cross section subtracted integration of p dx dy over area A. Now we know that P is equals to 0 on boundary. Therefore this goes to 0, this goes to 0, and what we have is 2 pi dx dy. So we have obtained the relationship between torque, which is equals to 2 into integration of p dx dy. Now consider this rectangle. This is the cross section. This is x, this is y, and if phi is the function like this, then the surface phi can be drawn as shown. This integral represents the volume enclosed between phi surface and xy plane or cross section. Therefore, torque is equals to 2 into volume bounded by phi surface and xy plane. Next point about this cross section is that on the boundary perpendicular to this boundary there is shear stress tau zr which is equals to 0. So perpendicular to boundary, shear stress is equals to 0, and if torque is applied in this direction, the shear stresses acts along the boundary. Shear stresses acts parallel to the boundary of cross section. So in case of rectangle, this is y. So if we plot P like this, then this is the angle alpha, and tan alpha is equals to dou P by dou x, which is equals to minus of tau yz. So at this point we can calculate this tau yz using this angle alpha, and this is the surface P. Similarly for y-axis, this will be the angle alpha 2, then tan alpha 2 is equals to dou P by dou y, which is equals to tau xg. So we can get the magnitude of tau xg. So depending upon the sign of this tau xg, the direction of the arrow will be shown. Now after this we will start to look how to solve problems for different cross section area, and we'll consider one example, elliptical section. So consider this is the cross section area, this is x, this is y, and this is the elliptical section. This is the A major, semi-major axis, and this is B. Then we know the equation of ellipse given by x square by a square plus y square by b square, which is equals to 1. Now this boundary y, this y can be given by a square minus x square b by a. Now how to consider p? So p is equals to 0 on boundary, therefore for ellipse we can write it as phi equal to m into x square by a square plus y square by b square minus 1. So this term ensures that p is equal to 0 on boundary. So we know this equation, dou square p by dou x square plus dou square p by dou y square, which is equals to minus 2g theta. So if we differentiate this one, we get 2m by a square plus 2m by b square, which is equals to minus 2g theta. So m is equals to minus g theta a square b square divided by a square plus b square. Also we have seen, if you know p, we can evaluate torque, which is given by integration over area A of p dx dy, which is equals to 2 into minus a to a minus b by a square minus x square minus plus b by a root a square minus x square m into x square by a square plus y square by b square minus 1 dx dy, which can be written as 2 into 2 0 to a and 2 into 0 to b by a root a square minus x square m into x square by a square plus y square by b square minus 1 dx dy. Now this we can divide this integration into different parts. I1 is equals to 8m into integration of 0 to a 0 to b by a square minus x square by a square dx dy. I2 is equals to 8m 0 to a 0 to b by a root of a square minus x square, and integrand is x square by a square dx dy. Sorry, this is y square by b square dx dy. Third integration is minus 8m into 0 to a 0 to b by a root a square x square dx dy. So we'll solve first integral. Eight m 0 to a 0 to b by a root a square minus x square by a square dx dy. We can write this as 8m to 0 to a by a square, then x square into b by a root a square minus x square dx. If x is equals to a sin theta, dx is equals to a cos theta. X square is equals to a square sin square theta. If x is equals to 0, which implies that theta is equals to 0, x is equals to a implies theta is equals to. Let's use these values in I1. So I1 becomes 8m by a square into b by a integration of 0 to a. X square is this one, so a square sin square theta, then a square minus x square is a cos theta, and dx is equals to a cos theta d theta. We can write it as 8m by, this is 1, this is 1, ab 0 to a sin square theta cos square theta d theta. We know sin 2 sin theta cos theta is equal to sin 2 theta, and sin square theta is equal to 1 minus cos 2 theta divided by 2. So I1 becomes 8m ab 0 to a sin 2 theta square divided by 4 d theta. I1 is equals to 8 m ab by 4 0 to a 1 minus cos 4 theta divided by 2 d theta. So this becomes 8 m ab divided by 8. Sorry, I have not changed the limits here. We need to change limits. This is 0 to pi by 2, 0 to pi by 2, and 0 to pi by 2, 0 to pi by 2. Here we can write it as pi by 2 for this first term, and second terms can be 0. So what we can write it as, this is gone, this is gone. So 2m pi a b by 4. I1 is equals to 2m pi a b by 4. Similarly, second integration is I2, which can be written as 8m double integration of y square by b square dx dy. Here it is 0 to b by a root a square minus x square, 0 to a. Now it becomes 8m into 0 to a y cube by 3 0 to b by a root a square minus x square dx. It can be written as 8m into, here b square is missing, b square, okay. So 0 to a b by a root a square minus x square whole cube, and then 3 is outside. Again we'll put x is equal to a cos theta, then dx is equals to minus a sin theta d theta. So when x is equals to 0, theta goes to pi by 2, and x is equals to 1, sorry, x is equals to a, it goes to pi by 0. We can write it as 8m3 8m by 3 b square b by a cube integration of pi by 2 to 0 minus root a square minus a square cos square theta cube a sin theta d theta. let m b by 3 a cube. So 0 to pi by 2, this becomes positive. A sin theta cube into a sin theta d theta. So this means this is gone and a remains. So 8m ab by 3 0 to pi by 2 sin 4 sin raised to 4 theta d theta. So we know sin square theta is equals to 1 minus cos 2 theta by 2. So sin 4 is equals to 1 by 4 into 1 minus 2 cos 2 theta plus cos square 2 theta. Therefore I2 can be written as 8MAB divided by 3 1 by 4 0 to pi by 2 1 minus 2 cos 2 theta plus cos square 2 theta into d theta. Now this cos square theta can be written as 1 plus cos 2 theta divided by 2. Therefore cos square 2 theta can be written as 1 plus cos 4 theta by 2. Putting this value in I2, we can get 8MAB divided by 3 into 4 0 to pi by 2 1 minus 2 cos 2 theta plus 1 half plus cos 4 theta by 2 into d theta. So 8MAB divided by 3 into 4 0 to pi by 2 1 minute. So this 1 is pi by 2, this is sin 2 theta by 2 and sin 2 theta limits are 0 and pi, so it goes to 0. This one goes to pi by 2 plus pi by 2 into 1 by 2. Again this term goes to 0. So what we have here is 8MAB by 3 into 4 and pi by 2 plus pi by 4, which can be written as 3 pi by 4 8MAB divided by 3 into 4, which is 2. This is 1, this is 1. So again 2m into pi AB by 4. Moving to next integration I3, which is minus 0 to a 8m 0 to b by a root a square minus x square, and integrand is what? Dx dy. Minus 8m into 0 to a b by a root a square minus x square into dx. Again similarly we can use x is equal to a sin theta, dx is equals to a cos theta, x is equals to 0, implies theta is equals to 0, x is equals to a, implies theta is equals to pi by 2. Therefore I3 is equals to minus 8m into 0 to pi by 2 b by a, then a cos theta for this term, and dx is equals to a cos theta d theta. Again mb by a square integration of 0 to pi by 2 cos square theta d theta, cos square theta is equals to 1 plus cos 2 theta divided by 2. Therefore I3 is equals to minus 8m AB integration of 0 to pi by 2 1 plus cos 2 theta divided by 2 d theta minus 4m AB into pi by 2, then this becomes sin 2 theta by 4, sin 2 theta by 2. We have already taken 2 outside and got this minus 4, and hence that next term becomes 0. Therefore I3 is equals to minus 4ab pi by 2, which we can write it as minus 2m pi ab 2m by ab, right? So let's add all these equations to get the I1 is equals to 2m pi ab by 4 to pi ab by 4. I2 is equals to 2m pi ab by 4 plus pi ab by 4 minus pi ab, which gives minus m. This is half, minus half. This is half minus half to 1 pi a b. we already know value of m. So I is equals to g theta a square b square minus g theta a square b square divided by a square plus b square into pi ab. Therefore torque T is equals to pi g theta a cube b cube divided by a square plus b square, which is equals to minus m pi ab. Therefore m can be written as m is equals to minus t by pi ab. So we have written our Prandtl stress function in terms of m as x square m into x square by a square plus y square by b square minus 1. Now we'll write this m in terms of applied torque T, which can be given as minus t by pi ab into x square by a square plus y square by b square minus 1. And we know that if you know Prandtl stress function, we can derive shear stress. Shear stress is tau xg and tau yg. So tau xg is given by dou phi by dou y, which can be written as minus 2ty divided by pi a b cube. And tau yz is given by minus dou phi by dou x, which can be written as plus 2tx divided by pi a cube b. So if we draw the diagram of cross section, this is the distance A, this is distance B, this is x-axis, this is y-axis. So we can see tau xg, which acts in positive direction, is given by this arrow. This is positive, and our applied torque is like this. So this tau xg is dependent on y, and maximum value of y can be found at this point. So tau xg maximum at z equal to 0, x equals to 0, y is equals to b, is written as minus 2t into b divided by pi a b cube, which is written as minus 2t by pi a b square. Now note that this sign is negative, so shear stress is negative. That means the direction of this tau xg is this, at this point. Similarly, tau yz at tau yz is dependent on this x, and x is maximum at this point. So what we can write is as y is equal to 0, x is equals to a, which can be written as 2t into a divided by pi a cube b. So 2t by pi a square b. So comparing these two, we can see that tau yz max is smaller than tau xz max. Therefore, we can see that the shear stress which is at this point is larger than shear stress at this point. In case of circular cross section, maximum shear stress was present on boundary at maximum distance, but here we can see that this distance is larger, but maximum shear stress present to the boundary where it is closest to the center. Maximum, therefore we have found maximum shear stress in elliptical cross section. In this way, we have completed our lecture on torsion of non-circular shafts. We have derived the equation for torque, shear stresses, and we have seen Prandtl stress function, how to use it to get the solution of shear stresses at different points on the cross section. We also seen the example of elliptical cross sections. So in this way we have completed our torsion lecture, and see you in the next class.